Two students are discussing angular momentum, clay ball, ceiling fan. Ceiling fan's not rotating prior to impact, but will rotate after the impact. And it says the clay ball ceiling fan gained angular momentum, so the system gained angular momentum. Elsa says there were no external forces, so angular momentum is the same both before and after the collision. Which girl do you agree with? Well, we did not gain any angular momentum. The system's closed. Clay ball, ceiling fan system. I do agree, so I'm putting a check mark next to the end of Elsa's. Which girl do you agree with? Explain your reasoning. Well, if an object's moving in a straight path, and if you look at its line of action, or if you draw a line along its path, and then it has a radius to a pivot point, its angular momentum can be calculated as mass, velocity, radius, MVR. And that is because it can cause that angular momentum to happen in the object that's not moving or change the angular momentum of another object. It too must have angular momentum. That's the only way angular momentum can be conserved in a system. At the end of a star's life cycle, they collapse inwards on themselves, gases and materials becoming concentrated around the center. What can we assume happens to the moment of inertia and the angular speeds of these stars? Please explain thoroughly. Angular momentum of a system is conserved. L naught is equal to L. Angular momentum is calculated as rotational inertia times angular velocity. Well, if the star is collapsing in on itself, the radius is getting smaller. If the distribution of mass is smaller, the rotational inertia is also smaller. It's basically mr squared. The r squared is getting smaller. So if the rotational inertia is getting smaller, the angular velocity, the omega, must be getting larger. Figure skater drawing her arms in spins faster. To conserve the angular momentum, if I goes down, omega must go up. Two drones fly into a windmill as shown to the right. Which drone will cause a greater torque to the windmill? We got to number these. Number 1 at the top, number 2 underneath it. Number 1 is the only one that's even causing a torque, so the only one that's a non-zero torque is number 1. It's hitting the windmill with a force from some distance away from the pivot. Number 2 is doing no torque because it's parallel. The moment arm is parallel. It's really force times radius times sine of the angle here. You're not getting any torque for number 2. If the windmill was initially rotating clockwise, what would be the effect of the drone's impact having the angular speed of the windmill? Number 2, it's not going to have any effect. Number 1, it's going to slow it down. It's going to cause a negative angular acceleration. So reduced. Explain how and when to use equation L equals MRV. Angular momentum being MRV is for an object moving a straight line where its line of action has some radius to a pivot point. So if you just draw out, just dot line, the straight line of action, the motion it's going to be moving in, its path, if it has any distance to a radius where it can impact something causing rotation, you take its mass times its velocity times that radius, and that's the angular momentum for that object. And if it's the only object moving in the system at that moment in time, that's the total angular momentum of the system then. Ben is showing his friend Carson the brand new motorcycle he just bought this day. While admiring this dangerous vehicle, they have discussion about rotational kinetic energy, or KROT. I can use KROT to help me go up an incline. Wow, any incline at all? Well, no, only inclines with friction. Explain why Ben says he can only go up inclines with friction. If you don't have friction, you don't have a torque, in this case, between the wheel and the ground. With no friction, no torque, you can't change the angular velocity. So the wheel will spin, but not allow you to convert out of that spin into some other energy. So the KROT stays KROT. You're not going to convert it to gravitational potential energy. Propose a way to test the following hypothesis. The motorcycle can travel up a slope with friction. Well, if you get the back wheel up off the ground and you have it spinning, the only energy you have is KROT. And then when you drop the back wheel, if it climbs up the hill, you're converting that KROT up to UG. If it doesn't climb the hill, you didn't convert the energy. So I would say get the tire spinning, rev it up, get the tire spinning, stop revving and drop the wheel. And it's not going to climb much because there's other factors involved. But if it's able to climb the hill, you've converted those energies.